Okay, so next exercise 22. Express -7 minus 3i to the power -1 in the standard form. A complex number is said to be in the standard form if it is expressed in the form a plus ib, where a and b are real. We have -7 minus 3i to the power -1 is equal to, it's just the reciprocal of -7 minus 3i. So in this situation, what you do, you have to multiply and divide by the complex conjugate of the denominator. So the complex conjugate is -7 plus 3i, minus 3i times -7 plus 3i. This operation turns the denominator into a real number because it becomes equal to this, and that is so because if say you have the complex number z is say this complex number, if we multiply it by its complex conjugate, then we get square of the absolute value, which is a real number, in fact a non-negative real number. So that's why we do it. -7 plus 3i. Now -7 square is 49 and 3 square is 9, so this is 58, and you can write it in the standard form like this: real part plus I times imaginary part. So this is the standard form. Then exercise 23, this is also similar. Express -5 plus 2i divided by 4 minus 5i in the standard form. Same procedure is same. You have to multiply and divide by 4 plus 5i, and then you have to simplify and find the standard form. So this I leave to you. Do it yourself. Then 24. Express cos 360 degree plus I sin 360 degree whole to the power 1 by 8. In the standard form without trigonometric expressions. note that the complex number cos 360 degree plus I sin 360 degrees is equal to 1. So this is the standard form, in writing which we haven't used any trigonometric expression. Exercise 25. Prove that for any positive integer in cos theta plus I sin theta whole to the power 1 by n is equal to cosine of theta by n plus I sin of theta by n. Okay, now there is a slight confusion about this exercise. We know that a complex number does not have a single nth root. It has n number of nth roots, and they are usually not equal. I think they are never equal. I mean, they are all distinct. So what is this equation telling us? It is saying that this is an nth root of cos theta plus I sin theta. That is the only thing it is saying. Okay, this is an nth root of cos theta plus I sin theta. This equation does not mean that this is the nth root of cos theta plus I sin theta, because this is not the only nth root. It's only one of the nth roots, n number of nth roots. So in that sense, it has to be interpreted. The author should have made this more clear. It's a little dissatisfying. Anyway, so in the text we have seen de Moivre's theorem. So we have by de Moivre's theorem. I may have written this spelling wrong. Okay, if it is wrong, correct it. By de Moivre's theorem, that cos theta by n plus I sin theta by n whole to the power n. N is a positive integer, so we can apply de Moivre's theorem. This is equal to cos theta by n times n plus I sin theta by n times n. So that clearly is equal to cos theta plus I sin theta. It tells us that the nth power of this complex number is equal to cos theta plus I sin theta. So by the definition of nth root, this complex number is an nth root of cos theta plus I sin theta. Hence, actually that should be written in language. However, with our interpretation of this equation, we can just simply write it. It should not be written in this form, but what can we do? Gallian writes it this way: sine theta, this is equal to ideally this expression is not a single complex number, it's a set of complex numbers, namely the set of all nth roots of this complex number cos theta plus I sin theta. As such, we should actually write this belongs to this set. Okay, that's what we should write. But here the solution ends. Okay, next exercise 26. For every positive integer n, prove that this. So this is a situation where we can easily apply induction on n. For n equal to 1, the left hand side of the given identity, if n is 1, the left hand side, the sum has only one term, which is 1, is 1. And the right hand side is 1 times 1 plus 1 divided by 2. So that is also equal to 1. So when n is 1, the identity is true. Now assume that the identity is true for some positive integer n. That is, we are assuming this. Then we calculate this sum, which has one term more than this sum. So by applying the induction hypothesis, this part of the sum equals n times n plus 1 divided by 2. Now if you take n plus 1 divided by 2 common out, then we are left with n plus 2. Okay, you just multiply, apply the distributive law. In the first term will be n times n plus 1 by 2. In the second one, 2 and 2 will cancel out. We will be left with n plus 1. And this is equal to n plus 1 times n plus 1 plus 1 divided by 2. So from the form of this expression, we can clearly see that in the case where we have n plus 1 terms, the identity is also true. This identity actually comes from an observation of the mathematician Carl Friedrich Gauss when he was a toddler he was a student in elementary school. The teacher asked Gauss to, not Gauss but all the students, to calculate this sum. It was a homework for the entire summer vacation. Gauss was able to calculate it instantly by recognizing this pattern. He thought of this way of rearranging the terms. 2 plus 99 plus, if you continue like this, say you take 1 and with 100, then 2 with 99, then 3 with 98. In this way, if you continue, you will eventually reach 50 plus 51, because you are considering terms which are closer and closer in this sum, okay, according to their arrangements. Now this sum is 101. This is also 101, because all you are doing is you are shifting a 1 from the second term to the first term. This decreases by 1, this increases by 1, so the sum remains the same. And since if you calculate these terms, there are 50 terms. So this is 50 times 101, and that is equal to 5050. Instead of using induction, this formula can also be proved directly by some such method. It just shows how quick Gauss's brain was. Even at that tender age, he was able to recognize such patterns and get the calculation done instantly, almost instantly. Okay, then exercise. I am particularly very bad at these calculations with actual numerical, actual numbers. I would require to write numbers and then only I can find the sum, product, whatever it is. I am particularly bad at this. For every positive integer n, prove that a set with exactly n elements has exactly 2 to the power n number of subsets counting the empty set and the entire set. Yeah, of course, because they are after all subsets of the given set. Now this is an exercise that we have already solved, and so since there is no point in repeating it, so I would ask you to watch part 8 from the playlist. If you look at the channel, you will see there are videos, playlists, many categories are there. You click on the playlist, there you will get different playlists where the videos have been categorized separately. Like for example, Herstein's Algebra has the videos related to that belongs to a playlist. Like that, Tau's analysis has its own videos in some playlist. So like that, you will find a playlist with this name. Topics in Algebra. Herstein set theory, I think. Yes. There you watch part 8. In that video you will find this solution. Exercise 28. Prove that two to the power n times 3 to the power 2n minus 1 is always divisible by 17. Okay, they have simply written always divisible by, so we have to take the largest possible variation of n, that is the smallest possible value of n that makes sense has to be taken. That means we have to start n with 0, because even in that case this is an integer, so we can see whether it's divisible by 17. And of course, to solve this exercise we will use induction on n, that is the easiest way. But you can also do without using induction. However, then you have to apply some results from number theory. So we are not doing that. Induction is the easiest. We apply induction on n. Note that 17 divides 0, which is 1 minus 1, and that is 2 to the power 0 times 3 to the power 2 times 0 minus 1. So when n is 0, the corresponding number is divisible by 17. So this is the basis for our induction. Assume 17 divides. Now we assume the induction hypothesis. This for some positive integer, or not positive, for some non-negative integer. Let us just write integer n greater than or equal to 0. When you make the induction hypothesis, you have to include the basis case. In case you plan to use n plus 1. So if you are assuming that something is true for n, where your cases are starting from n equal to 0, then you have to take n greater than or equal to 0. If it is starting from 1, you can take n greater than or equal to 1. For some integer n greater than or equal to 0. But if that is the case, then this will be a multiple of 17. So let this be 17k, where k is an integer. Actually k will be a non-negative integer, but we really don't bother about the sign of k. Well, the only thing is that k is an integer, and as such this is an integer multiple of 17. That's all we need for this solution. Then now in place of n we put n plus 1. So this becomes equal to, is it better to do the calculation below? Two to the power n plus 1 times 3 to the power 2 times n plus 1 minus 1 is equal to, we can just write the entire expression like this. Now 2 times 3 square is 18. So 18 times 2 to the power n times 3 to the power 2n minus 1. So this can be written as 17 times this plus another 1, another 2 to the power n times 3 to the power 2n, and we have minus 1 additionally. Now from our induction hypothesis, this is 17k, and so we can take 17 common out. Now this is an integer, so 17 also divides this one, which implies (17) divides this number as well. This completes the induction and the solution. Okay. Then exercise 29. Prove that there is some positive integer n such that n plus 1, n plus 2, like this, all the way up to n plus 200 are all composite. Okay, so for some choice of n, all these numbers will be composite, which are, if you see, 201 consecutive integers. Take n equal to 202 factorial plus 2. For this value of, actually there are many other values also, this is one of the values. For this value of n, what happens to n itself? Is it composite? Yes, because it is divisible by 2 and it is not equal to 2, it is greater than 2. That is because if you expand 202 factorial, in that expansion 2 is a factor, so you can take 2 common out, and clearly this is greater than 2, so that's why this is a composite integer. If you add 1 to it, you will have 202 factorial plus 3. Since 202 factorial also has 3 as a factor in it, so you can take 3 common out, and n plus 1 is also greater than 3 because it is 3 plus something, and that something is positive. So n plus 1 is composite. Similarly, n plus 2 will give you 202 factorial plus 4. So you can take 4 common out, and so it is divisible by 4, but at the same time it is greater than 4, so it is also composite. Like that, all the way up to n plus 200. In this case, you will have 202 factorial plus 202. So you can take 202 common out. So that means this is divisible by 202, but at the same time it is not equal to 202, it is greater than 202. So this is also composite. You can write these things. Okay, I am not writing the entire solution because it's understood how it has to be written. For this choice, all these numbers will be composite. Now the interesting thing here is that, do you see, you can take, instead of 200, any number means, say for example 200,000 or 2 million or 2 billion, and even then you will be able to find, by conveniently choosing this number n, such an n for which all such consecutive integers will be composite. In other words, in the sequence of positive integers, you can find a finite part consisting of consecutive integers that are all composite. That place is devoid of primes. So in this way you can create arbitrarily large finite gaps, of course, in the list of prime numbers between two primes, and that says something very that gives us a vague idea of how prime numbers become more and more sparse as we go down the numbered line. Okay, then exercise 30, generalized Euclid's lemma. Okay, that is its name. If P is the prime and P divides A1, A2, etc. up to A, and P divides this product where they haven't mentioned what these a1 a2 are, but we can understand since division is there, so these are integers. Okay, a1 a2, these are all integers. If p divides a product of any number of integers, prove that